Hi physical science students, welcome to the next video in the series of covalent bonding. This one we're going to talk about electron dot diagrams. Now electron dot diagrams are important because we use them for representing what's happening in the bonding in covalent molecular substances. And so we need to be able to represent the bonding and also the covalent bonds. They're a way of simplifying the drawing of atoms. They're sometimes referred to as Lewis diagrams and also valence shell dot diagrams. But electron dot diagrams or Lewis diagrams are the most common way they're referred to. And we're only representing the outer shell electrons. So it's a way of simplifying the drawing of atoms. Instead of drawing all those circles and lots of dots, we simplify it down because basically chemistry is about what's happening with the outer shell electrons, the inner shell electrons, and the nucleus are all pretty happy. And so this is a way of also drawing atoms but also molecules, and by the end of this video you should be able to draw both atoms and molecules using electron dot diagrams. And it's a good way of developing how to show covalent bonds. Now in an electron diagram we simplify it by basically representing the nucleus and all the inner shell electrons by the symbol. So the symbol, instead of drawing all those circles and drawing the nucleus, we just write the symbol because we're really only interested in the outer shell electrons. The outer shell electrons are then represented by dots around the symbol in a square arrangement. Sometimes people think of it as a circle, but it should really be a square with four sides. And the dots are arranged in twos, and if there are more than four outer electrons present, you've got to make sure you fill out the dots correctly, and we'll go through that. And I'll show you what that means. And for example, nitrogen with 4 electrons in the outer shell, how are we supposed to represent that? Well, this is an example. There's our nitrogen, there's the nucleus and the inner shell electrons. 5 electrons in the outer shell, and we would draw an imaginary square there, and we've got 4 sides, so we draw 1, 2, 3, 4, and then we put the 5th one there, and I'll go through that again in a sec with sulfur. And it's important we get this arrangement here because what we want to know is that here we have a pair of electrons that won't be involved in bonding. And they're called the non-bonding electrons or lone pairs, whereas these 3 electrons are the bonding electrons. So that tells us automatically that nitrogen needs 3 bonds for it to get a full outer shell. It needs to share 3 more electrons to go from 5 to 8, and to get those 3 shared electrons it's got to form 3 bonds, and that's why we have these 3 single ones here. And I'll quickly go through the technique of how we work that out. And we'll use sulfur as an example. Its electron configuration is 286. So we're not worried about these 10 electrons here, we're only worried about the outer shell electrons. You write the symbol S. Hopefully we memorized our symbols, or we can look it up in the periodic table. We're ignoring the inner shell and the nucleus, and so we fill in the outer shell going clockwise. Now if I click this, something should happen. There's our boxes that we would put dots in representing the electrons, and there should be 8 positions where they can go because there's potentially 8 electron outer shells. But where do you put the dots? Well, typically you would follow this order: 1, then the next one there, then the next one there, 4, then 5, and so you fill in going clockwise. Can go anti-clockwise if you want to be an individual. Doesn't really matter that much. And that way, if you follow this technique, you'll be able to then identify how many single electrons there are and how many bonds the atom needs in terms of covalent bonds. Like when we did nitrogen, by having 5 electrons we could see that the 1st and the 5th one go there and form the lone pair, and we're left with 3 single electrons, and therefore 3 bonds are needed. That's how you tell. So sulfur, let's just see what happens here. If I click this, this is how we're going to put in the 6 electrons. Dot, 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 dot. And that's it. There's our 6. So we have 2 lone pairs. There's a lone pair, there's a lone pair. Now these single electrons tells us, if we hadn't already known, by looking at the electron configuration, it tells us that sulfur needs 2 covalent bonds to be happy. Has to share 2 more electrons to get the full outer shell. Okay, now there is no hard and fast rule as to where you put all these dots and things. I've shown you a way that will give you consistent results. However, you could also draw sulfur like this, and sometimes it is valid to draw it like that, because when you want to draw sulfur bonded to something and you want to have the covalent bonds distribute themselves evenly and symmetrically, and that's what actually happens in molecules. So you might use this technique to work out how many bonds you need for sulfur, but then when you draw your molecule you can move them around as long as you're keeping the 2 single electrons. So here's a whole lot of diagrams of some of the non-metals. There's carbon, 4 valence electrons, we draw 4 dots, 5, and you can see they filled it in. In this case I think they've gone anti-clockwise, doesn't matter. And then fluorine has 1 lone pair, and here they've put a table of lone pairs versus bonding. So make sure you understand the difference between lone pairs and bonding electrons. And neon has 4 lots of lone pairs and no bonding, so it doesn't undergo much in the way of chemistry. So you've got to do this question in the table. I've already effectively done most of it for sulfur. We've worked out that, let's just see if I can draw today. It's so slow. There must be so many things happening to this poor old computer. Let's go green. So we've worked out that sulfur has 6 electrons, and so we would draw it as dot, 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 dot. That's a bit messy. I can tidy that up a bit, as we all would. Okay, and so in terms of lone pairs we've got 2, and in terms of bonding electrons we've got 2. Remember, the lone pairs equals 2 electrons in each pair. That's why it's called a pair. Okay, now you work through that. I'm just going to get rid of this writing and get this back, and then theoretically perhaps the answers appear. There we go, and if I click on this, voila, they're the answers in the back of the book. So you're going to have a go at this question at the end of this video in class, and hopefully you'll get those answers. Make sure you check them, make sure you can do everything okay. Now the rules for drawing electron dot diagrams for molecules. So just then we just learnt how to do them for atoms. Now we need to be able to put those diagrams together to make molecules. And there's some rules, and I'll go through them and then you can have a double read through them. These are also in your textbook. Draw the dot diagrams for each of the atoms in the molecules. So we should be able to do that now. Unpaired electrons, the bonding electrons, are available for making a covalent bond. So that tells us how many covalent bonds we need. Paired electrons, or the lone pairs, do not. So we don't count those in terms of the covalent bonds. The atom with the most bonding electrons, so the most single electrons, once we've drawn our diagram, is called the central atom. And we put that center and then we put the other atoms onto it to form the covalent bonds. In the resulting diagram, all electrons must be paired. So we have to have all pairs. Can't have any single electrons in covalent molecular substances because there's no charge imbalance. Everything neutralizes. So we must make sure it all adds up. So let's do an example. Chlorine is Cl2. There's our electron dot diagrams for the 2 chlorines. Notice that in this case I've used dots and crosses. Crosses are okay. If you've got one of those fancy pens with 4 colours in it, you can use dots or crosses, different colours. You can go crazy if you want. So there are our electron dot diagrams, and looking at those automatically you can see that there's a single there and a single there, and both chlorines just need 1 shared electron to make a full outer shell. So we're going to get 1 covalent bond, and so we would draw it like this with the 2 next to each other. sometimes students, let's get this pen working, a common mistake is to draw it. If we go chlorine and chlorine, and they put a dot there and they put a cross there, and that's a bit lazy if we're to be honest, okay, because what it's not really showing what should be happening, and what's happening is this electron is not closer to this nucleus, and this electron is not closest to this nucleus. They're being shared, and they actually move between completely. They're not owned by any individual atom, and so just be careful about that. Let's get this back. I'm doing a bit of drawing, which slows us up. So there's our electron dot diagram, and that's what it looks like. And if we were actually to simplify it, the next step to simplifying it would be just to write Cl with a line between it and Cl, where that is our covalent bond, and that is equal to one pair of bonding electrons. I'm doing running, fantastic. Okay, so if you're asked for an electron dot diagram, you've got to draw that. But if you're just asked for the bonding or a representation of the molecule, you can just go and draw the covalent bond, because everybody knows that all the other lone pairs are there and they're happy. No one's worried about it. Alright? I think if I click, something else happens here. Let's see. Come on, old computer. There we go. Space filling model of Cl. So that's what it looks like in terms of space, how much space it occupies. And there's our covalent bond. Sometimes also referred to as just drawing the structural formula. So when we go and do organics, we draw a lot of structural formulas where we just use lines to represent the covalent bonds, and we don't show all the rest of the noise because it gets in the way of our complicated diagrams. Let's do another example. Excuse me. Fluorine, F2. Here we go. This is the old hand way of drawing it, where we've drawn in a shell and we've drawn lots of dots. Takes forever. There's our pair of shared electrons. Here is our electron dot diagram indicating it. Here's a sort of compromise where they've drawn the electron dots and then they put a covalent bond in there, and then they've drawn the electron dots. I would probably recommend that we don't draw the pairs there. It's just the way we draw it here in Tasmania. This textbook does that. And this is the ball stick, and this is the space filling model of it. So make sure you understand what they've done there. And remember, if we were asked to draw a structural diagram of it, we would just write F like that. No dots. Okay. Let's just move on. A couple more examples, I think. Oxygen. Okay, same textbook, so they've got the same idea here. Now in this case they've drawn the pairs because oxygen needs to have two covalent bonds. And if we were to draw just the oxygen, let's change the colour. If we were just to draw the oxygen Lewis diagram, we'd go 1, 2, 3, 4, 5, 6, and there's our two lone pairs, and that tells us we need two bonds. So that would be one bond, and that would be another bond, and we're representing it here just as two straight lines. So in Tasmania, we'd be happy for you just to draw it like that. Okay. So hopefully we've got the idea. They get a bit complicated with more than one bond, but it sometimes just takes a little bit of practice to get your head around it, and then you can do it in your head. So show the bonding between two oxygen atoms. There you go. Now notice they've rotated the diagram so that two lone pairs. They've drawn this, and then they've recognised that they've got to go in pairs, and they've also made sure that there's a pair and there's a pair. And this is probably a better way of drawing it than having the dots like this, or if we were using this, they'd have it like that. Okay, that's not the best way of drawing it. This is much better. So try and just remember to do it like that. Alright, so you should now be able to read that. Doesn't tell you much. There's our structural diagram, which we drew before. So you should now be able to do question 2, 3 and 4 in your chapter. Any tricks to those? Nitrogen takes a little bit of practice. Then you should be able to work out that. Draw the electron dot diagram structural formula for fluorine. I've already given it to you. Which of the following substances contain discrete diatomic molecules? So for them to be molecules, they've got to be non-metals, bonded, and you've got to have more. So anything that's ionic, for example magnesium oxide, doesn't have molecules. So think about what all these are in terms of our classifications and whether they have molecules or not. And the answers will quickly appear. There they are. They're in the answer to your book. And let's do some molecules. So in this case carbon dioxide. So you've got your carbon. It's got the most single electrons, 4. Oxygen we've drawn before. We recognize that we need 2 of these because each of these needs 2 bonds. There's one, there's one. This needs 2, there's 2, there's 2. So it takes a little bit of mental arithmetic or gymnastics to recognize that you need to draw it like this. And notice that they've also swung these pairs away instead of drawing them there and there, because that's what actually happens in the molecule, is that these electrons are repelled by these electrons and they distribute themselves evenly. And there's our structural formula for it, which looks a little complex, but basically it's showing 2 covalent bonds there and 2 covalent bonds there. Water, H2O, there's our oxygen again, 2 bonds needed, hydrogen, 1 bond, and so we can draw it there and there. In this case they've done something weird. Just because it's water, they've shown a structural bond there and there. I would recommend that you don't do that, and so we would draw our structural formula for water as something like that. Okay, you can be tricky if you want and put it like that. Recognizing that this is a 2-dimensional representation of something that's actually 3-dimensional, and so we are making compromises with our drawing anyway. But we recognize that. Alright, what happens now? Methane, so carbon with 4 hydrogens, looks like this. We draw it like this, but this is a 3-dimensional representation. You can see the bonds would actually be representing themselves. If that's our carbon, we'd have bonds representing themselves into a tetrahedral, if I drew this correctly. Okay, so, sort of like a pyramid with a triangle as its base. So that's just how it occurs, but we're drawing them 2-dimensionally, so we don't have to worry too much about it. Ammonia, again they've drawn the lone pair there, but I wouldn't recommend that you draw that. And this is our electron dot diagram showing you 3 bonds needed to make ammonia. So you should now be able to do the bonding between hydrogen and bromine and oxygen and fluorine, and you should also be able to draw nitrogen fluoride. Let's just go back. No, I thought I might have actually given that to you already, but see if you can draw that. And the answers will briefly appear here, but they're also in the back of your textbook. Okay, no real tricks there. And then you should be able to do number 7. All those guys, they get a bit more complicated. Now, the only thing I need to suggest here is when you have carbon, carbon can form carbon-carbon bonds. And so think about that when you're trying to draw this and only get 8 hydrogens. Same with these two. The carbons will join together and form a chain. That's a clue, and the answers will briefly appear here. And there's our carbon chain. There's another 2 carbons joined together, 2 carbons together. So we should, when you're drawing your answers, they should look lovely like this, shouldn't they? So now you can do all these questions, and so in your OneNote this will be described to you. There's the page numbers for you, because everyone has trouble finding the pages where the questions are, And the next video we're going to look at is how we name covalent molecular compounds. So, see you next time. Cheerio.